swapping those two topics. So when you look at the schedule, I pulled C13 up in place of mass spec, and we'll do mass spec after amines. Okay? So, as far as C13 goes, you have a couple of assignments associated with it. If you look on D2L, you'll see a couple things. First of all, and hopefully people came in with them today, the C13 slides, the PowerPoint slides. And then there is a C13 worksheet plus answers. And this worksheet, we compiled it from a bunch of old test questions. So what you're looking at are like 5 or 6 exams worth of C13 test questions. And the answer key is up there for you to take a look at as you do it. So it's just a little bit more practice. Then in the quizzes is a C13 quiz. And I haven't made that active yet. You have, I don't know, 2 weeks at least, 2.5 weeks to get on there and do it. So sometime next week it will pop up, and in the unit schedule it tells you the date by which you need to go on and take the quiz. Mass spec is structured very much the same. There's a mass spec worksheet, which is a bunch of old test questions to give you more practice, and there's the answers. And then there's going to be a mass spec quiz as well. Okay, so rather than turning the worksheets to me, you'll just be taking the quiz. Okay? All right, then let's go ahead and let's start C13. We'll find my notes first. Most instruments, when you go into an NMR room, for example, like at Davis, they have proton NMR instruments, and those instruments are capable, with no major changes at all, of also running C13. It's just a question of hitting a button and telling it, yeah, I want C13 instead of proton. So the probe, which is the part of the instrument your sample drops into when it disappears into nowhere, it is our probe and our machine can only pick up proton. But most probes have a dual purpose. And we could have bought a dual purpose probe, but it was something, I think the cost, it was either $5,000 or $7,000 or maybe $13,000 to get a probe. Anyway, the school said, so we don't have a C13 probe, which is okay, because as you're going to see in a minute, you know how long it takes all you guys to get through the NMR? C13 takes a lot longer to get a spectrum, so it wouldn't be practical for us anyway. But if you guys do research, there's no doubt you'll run into machines that can do C13. It's really standard. So, this first sentence is sort of a no-brainer, but carbon-13 NMR detects only one isotope of carbon, and that is, guess what? C13. So, with carbon, you have carbon-12, you have carbon-13, and you have carbon-14. Carbon-12 is the one that is the major one. So it's like, what, 99 point, let's just say 99%, that's close enough. It's 99% of the carbons out there. So most of the molecules that you have that you're doing NMR on contain carbon-12, which is not NMR active. Carbon-13 is about 1% of the carbon out there. Carbon-14 is just a trace. Where is carbon-14 used?
Dating.
In dating, yeah, carbon dating. It's just a trace. Dating. So, do you remember the criteria for an atom to be NMR active? What was the criteria?
Asymmetrical?
Had to spin, right? It had to act as a small, the nucleus had to act as a little rotating sphere. What caused that though? Not every the neighboring odd number of protons or neutrons. Remember that? Yes. So carbon has 6 protons. So this guy, carbon-12, 12, 6 protons, 6 neutrons. No go. Carbon-13, 6 protons, 7 neutrons. So it satisfies the criteria. The problem with it is that there's a really low abundance of C13. Most atoms in a molecule, in a collection of molecules, are not NMR active. They're C12. So what that means in the NMR, there's a very, very small signal. So you don't get much data from doing a scan of a collection of molecules when you're scanning for C13. So one scan gives you not enough information. You need more than one scan. With proton, we typically set it to 4. That's kind of our standard. Sometimes we go a little higher, 16 is a big deal. And that's, you're getting essentially 16 data sets out of that collection of molecules. And that's enough to give you a good spectrum. But that's not enough for C13 because there just are not enough atoms of a particular type to give you much of a signal. So you have to go over and over and over to get enough data to actually get an NMR. So typically, if your sample is really concentrated, which would be the ideal, a really concentrated sample, you maybe can get away with 100 to 200 scans. More typically, your sample's not that concentrated, and usually it takes thousands. So we'll go 1,000 plus. What I had to do, you remember we talked about my remarkable 12% yield, right? I got like 1 drop of material, was the most I ever got. And so I would put it in an NMR tube, which clearly is not concentrated. I would check out the NMR instrument late at night. And I would be there, and at about 9 at night, I'd put my sample in, and the number of scans you can set, if you type in NS, and you guys put in 4 or 16, you can type in -1. And that's code for go until I stop you. And it will just go, and it would go overnight. And so I'd come back, and I'd have, 10,000 scans, and get a reasonably decent carbon-13 NMR. So that's another reason we don't do it, is because if each of you had to take, let's see 100 scans, you could get, imagine, it would take us 4 or 5 weeks to get through an experiment. So, that is one of its downfalls, is you need a lot of scans to do it. Okay. So, let's talk about what you get when you do get a carbon-13 NMR. The energy range, remember the energy gap? We had the alpha spin state and the beta spin state when you put something into a magnet. And let's say your magnetic field is here. So that's your applied field. The alpha spin state was where the nucleus lined up with the magnetic field. And the beta spin state is where the spin lined up against the magnetic field. And if you remember in our conversation about proton NMR, you probably vaguely remember this, there's the energy gap here. And when the radio frequency that you're applying, which is the energy you're applying, matches that gap, then you can get a spin flip from alpha to beta. So alpha goes to beta when the gap is, or let's say when the gap matches the applied radio wave. Remember that discussion? Sort of vaguely? Okay. So you get a spin flip, and that's what you're measuring. The gap's different for carbon than it is for hydrogen. And so one of the things that we see happen is that the scale is a lot different. And hydrogen, a proton NMR spectrum, we went from 0, and this was parts per million, to 14. That's what we're used to. And there is an equation, I think it's given in your book, but it relates the scale down here parts per million has a relationship to frequency. So you could have the scale in hertz as well, but we don't because then it's instrument dependent. It depends how powerful your instrument is. So we normalize it. It becomes parts per million. So this has some tie-in to the energy gap. Okay? And for hydrogen, the ranges are 0 to 14. Well, for carbon, since the gap is different, the range is from 0, and we're going to use TMS, same standard. It goes from 0 parts per million to about 200 plus. The range is much, much larger. So that's one of the differences that you see, is that the chemical shift range is very, very much larger. Now, just like proton NMR, each type of carbon in an environment has a certain place that it has a chemical shift. So, start off to sleep. Let's take a look at the first slide right here. This gives kind of a range of where things are. This is a lot more complete than we need. But remember now we're focusing on the carbon. And so you can see that, oh, where's it going to break off? It looks sort of strangely shifted. Okay, there we are. I'm just going to get my pointer. Alkanes are kind of here, and I'm just going to point out some of the major ones. Alkanes are here, and then we have amines and alcohols. That's a carbon with an OH on it. And then we have carbons involved in benzene rings are right here. Double bonds are right in here. And then we have carbons as part of C double bond O's. They're kind of all in this range. So we have a very similar shift as we saw with hydrogen, in that the more de-shielded a carbon is, the further downfield it shows up. And the same factors that de-shielded the proton de-shield the carbon. So there's nothing new to know there. What you know about hydrogen, you can apply directly to carbon. Hang on a second, David. So more de-shielded carbons are further downfield. So the same trends that you guys have memorized apply directly over. Yes?
Why is it that the triple bonds come before the double bonds?
You know, I think you have the same, there's a factor called, when we've never talked about it, the anisotropic effect. And that has to do with in a pi bond, your electrons set up a current, and that current can sometimes reinforce the magnetic field. And so it most likely has to do with that. You guys only have to memorize the major ones, and I'll show you a table, I think is our next slide, that can be a little more helpful to you. Kind of gets rid of the clutter. Yes?
Shouldn't the carboxylic acid be the ketone and aldehydes?
Ketones and aldehydes have that anisotropic effect again. And so with the carboxylic acid, maybe this will help explain it. This might give us a hand. We're looking at this guy right here, right? And versus, let's do an aldehyde. This guy right here is de-shielded certainly by this, right? But this can actually donate in a resonance structure, and this one can't. There's nothing going on there. So you have the full force of the carbonyl here, and here it's mitigated somewhat by that. Okay. Let's take a look at kind of getting rid of like cell phones, because we don't care about them. That chart right there is pretty much what you guys are going to have to become familiar with. And the chemical shifts all follow the same trend, but the numbers are just bigger because we're going to 200 instead of the 14. So you can see alkane, just plain old alkanes are, I don't know, around anywhere from like 10 to about 30-ish. And then when you put halogen on there, it shifts it a little more downfield. When you have an oxygen, shifts it a little more. And then we saw where aromatics and those kind of things fall. There is a way that is kind of helpful to help you not maybe have to memorize all these numbers. And it works pretty well. It has some failings, but it works pretty well. And that is that the chemical shift of a carbon is equal to roughly, this is approximately, 15 times the chemical shift of the hydrogen, of a very similar kind of hydrogen. So as an example, let's say I wanted to know the chemical shift of that carbon right there. Well, the chemical shift of that hydrogen right there is about, I don't know, 1.2 maybe? Okay, so 15 times 1.2 is about, gosh, it's higher math, about 17 or so? 18. So it should be about 18. And if you look at the table, it ranges between 16 and 25. So 18 is good, it's about 20-ish. Okay, if you take a look at, let's do another one. Let's look at acetone. Okay, and let's say I want to know what the carbon is. Well, the hydrogen for acetone is 2.1 parts per million. So the carbon in acetone is just 15 times 2.1, or it should show up 30-ish. And if you take a look at our table, it shows a ketone. It's the fourth entry down, and the carbon next to the ketone is at 30. So you can take what you know about hydrogen, multiply it by 15, and roughly that will tell you where the other things go. Okay, so far so good? All right. Now, just like we saw with hydrogens, carbons can be influenced by their neighbors. So you see spin-spin coupling with C13 too. Spin-spin coupling was this. Let's look at hydrogens to refresh ourselves on this, and let's dive in. Let's put a bromine here. It's going to get too complicated. Okay, with spin-spin coupling, what we did with that is let's say we're focused on the CH3s. You had to look at the neighbors to see how they affected the applied field, and that caused this to get split in different places. There was a big long discussion we went through this last semester. The bottom line is, to figure out the splitting, what was the rule? Do you remember? N plus 1. Yeah, it was N plus 1, where N was the neighbors. Number of neighbors. So, this guy has 2 neighbors. It shows up as a triplet. The CH2, it has 3 hydrogen neighbors. It's a quartet. That's what spin-spin coupling is splitting. It's a fancy word for splitting. So, with C13 NMR, you potentially could be very sad. Because, let's drop the molecule in. CH3, let's make it a CH. Yeah, I'll make it CH2, CH3. C double bond O, ER. Okay, so the C13 atom is going to couple with whatever's NMR active. So you have 13C to 13C coupling. made it complicated enough. Right, but now it's 2 kinds. Okay, well, we're going to do some simplifications now. Tell me what the odds are of this happening.
Very slim.
Tiny, right? It's super, super slim because carbon-13 is only 1% of the possible atoms in your molecule. So the odds of having them lined up next to each other are really, really slim. When they are lined up next to each other, they couple. Okay, but the signal's really weak. And so the odds of this occurring is not likely. When it does, which it will, it's too weak to see. So it happens. When they're next to each other, it does happen. But as far as our ability to have to see it or worry about it, we don't care. Because we can't see it, so it's a non-issue. So we can kind of just go, who cares? Okay, that's not to say it's not happening, we just don't care about it. Okay, so we've narrowed it down to coupling we can actually see. And that is the carbon-13 hydrogen coupling. But to further simplify things, for reasons that are beyond me, there is extensive coupling with hydrogen. But it couples only with attached hydrogens.
Thank you.
I know. So that is not too bad. It's only going to couple with the attached hydrogens. So, let's see, I've got a number here I want to give you. With the attached hydrogens, so if I have, I'm going to give you some numbers here. And then we'll look at the neighboring ones. So here's our C13 right here. We're going to focus on this guy, this center guy. Coupling with the attached hydrogens, the coupling constant is pretty big. The coupling constant is 125 to 200 hertz. It's a big number. And if you remember, the coupling constant was, let's say you have a triplet. You have a triplet that looks like that. If I could draw a triplet, we'd be ahead of the game. The coupling constant is this distance here. J is the coupling constant. So it's the distance between the peaks. So with directly attached hydrogens, it's about 125 to 200 hertz. With hydrogens that are adjacent, neighboring ones, it's 1 to 6 hertz. Those tiny, tiny, tiny. And remember, our scale is really big. So any tiny, tiny, tiny splitting, you're not going to see. And so that's why you don't see it. So you don't have to even worry about it. So we're not going to worry about C13 to C13, nor are we going to worry about C13 to neighboring hydrogens. We only care about the attached ones. So let's take a look at a carbon-13 spectrum. They're beautiful. There's one right here. I like them because everything is so spread out. Our parts per million is 15 times bigger. And so the peaks you get much less accidental equivalency. You know, in the NMR, you guys are constantly getting blobs of overlap. It's not nearly as common here, these blobs of overlap, because it's so spread out. And also, because the coupling constant is giant, 125 to 200 hertz, then your individual sub-peaks get really spread out too. So quartets and triplets are beautiful. You can really, really see them. So if you take a look at this guy, right here, we'll start with A. That's just essentially an alkyl carbon. So it's going to occur in this region, down here where it's shielded. It has 3 attached hydrogens. So it is this quartet right here. And N+1 still applies. It's this quartet. So this right here is for A. Okay, what's another easy one? The one with the alcohol, D, right here. It's on the OH, and so it's very de-shielded. It's gotta be this guy, right here. It has one hydrogen, N plus one, it's a doublet. Okay? How about C, the CH2? Where is it showing up? Yeah, it's got two attached hydrogens, it's this triplet right here. This triplet. And then we have this CH3, right here, it's another quartet. It's more de-shielded than the A, so B is more de-shielded than A, it's gotta be this one. There. So it's really kind of easy when you see the splitting to identify what's what. Yes?
So the splitting for C, why is it further down than the CH3?
Oh, it is for, if you look at, this is, come back. C right here is the triplet, and it's a little further down. And then this one, they're both the same distance from the OH, right? It's a little more de-shielded. C is a little more de-shielded because there's an alkyl group attached.
Yeah.
So if you remember when we did proton, we had CH3, that showed up at about 0.9. And then when we had CH2, CH3, we focused on those, that showed up at around like 1.1. And it was a secondary. And then if you had something like this, hydrogen, and you had carbon, 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 that drove it down to, I think it was about 1.3. So as you attach alkyl groups, it gets a little bit more de-shielded. And the effect isn't very much, but it's somewhat. Okay, everyone all right with that? All right. Okay, now, you can, one thing we should point out too, the peak height. In hydrogen, we rely a lot on integration, right? But the peak height in proton NMR, and the peak, like the area, does not necessarily correlate to the numbers of that type of carbon. And so no one integrates carbon-13. It's just not done because it gives you data that makes no sense. It's not consistent and it fails. So we won't be doing any integrations. Okay.
But is there such a thing as environments, or?
Well, sure there are, because if you had, let's say you had something like this. Let's say I put a double bond O there. I have a carbon there,
Okay.
right? And these two carbons are the same,
You're gonna
right?
integrate
And if
them.
you tried to integrate them, you'd expect this to be twice as big as that. That fails. It doesn't work that
But
way.
it still overlaps though.
These two would still show up in the same
Oh.
place. Yeah. Yeah, so all those ideas still work, but just don't try to integrate. Now, you can imagine that if your molecule was complicated, something bigger than 2-butanol, that you could start to get some overlap. So let's say you had, I don't know, I think it was Tammy who did a lot of C13 on sea sponge juice. So they would go and they'd get sea sponges and squeeze them, I guess, I don't know what they did. But they'd get sea sponge juice and they would do C13 on them. Well, that molecule is big. I mean, it had, I don't know how many, 30 carbons in it. And you get them all split. And so all of a sudden you've got these big spread out quartets overlapping with big spread out triplets, overlapping with another big spread out quartet. It can get pretty messy because things are so spread out. And so what people will typically do is they will do a process called decoupling. So for this next topic is proton decoupled C13 NMR. And you're really going to like this. What you do, proton decoupled C13 is you remove all C13 proton splitting. So there is no more splitting. The triplets go away, quartets are gone, and what you see is you see single lines for each type of carbon. So essentially, the triplet, the quartet, they all collapse down and just give you a single line. There's no more splitting. And the way you do this, you remove the splitting by you send a pulse at the sample, the machine does, that causes the hydrogens to spin flip. So they end up, if they spin flip, they relax, they spin flip, they relax. So they end up plus minus, plus minus, plus minus, plus minus. What's the average of plus minus? Zero. They end up like they're not there. And so it's this broadband radio pulse that gets sent out that removes the coupling and everything collapses down to single lines. So the advantage of that is that you can tell how many different types of carbons there are, because the overlap is gone for the most part. And from the parts per million, you can tell the environment. So it doesn't give you quite as much information as when it's coupled, certainly, but sometimes coupling just ends up this giant blob of peaks overlapping, and it's not useful. So let's go ahead and take a look at the next one. It should be this guy, decoupled. There it is. So going back, there's the quartet, triplet, etc. And there it is decoupled. See how they stay in the same place. They're centered in the same spot. They just collapse down. And there they are side by side. So you guys can see the difference.
So they do where the highest peak is, or average them, or?
I think what they do is here's one end, here's the other. You take the average and go to the center. Because the peak is centered around a certain place.
Can you tell how many carbons?
And you can tell how many carbons there are. So I'd look at this. This thing at 0 is TMS. This TMS is still in the sample. And so what you do is you just come over here and you would count. You'd say 1, 2, 3, 4. Well, this molecule has 4 different kinds of carbons. And I can't, there's not as much information. I can't tell how many hydrogens are on it, right, just from this. But I can sort of tell, based on my parts per million, this thing here probably has an oxygen on it, based on my chart. I know there's something very de-shielding here. And this probably is just the alkyl part. There's not much on that. Okay, so you lose some information, but it's a lot simpler looking. Okay? So let's go ahead, and you've just learned C13, believe it or not, that's like it. So let's answer these questions here. And then we'll look at some spectra, and then we're done. So we're assuming here it's a proton decoupled C13 spectrum. So we are looking at lines. Okay, it's just going to give us lines. And I'm going to redraw the molecule so I can write on it. There it is. So how many peaks you would have depends on how many different kinds of carbons you have. So I have that. This clearly one type, right? This one is different. I'm going to run out of shapes. A triangle. That one's different. A square. Okay. That one's different. You guys are okay with those being the same?
Lion. Not a lion.
Those are different. I already liked it. It was short. This is oblong. A heart. I love it. There we go. So how many different kinds are there? 1, 2, 3, 4, 5, 6. There should be 6 lines. So, come on. Okay, there it is, right there. So there are 6 lines, and I wish I could blow it up, but you can see 0 didn't show up, so whoever ran this didn't have TMS in it. I think it's computer generated, actually. Hard to say.
Yeah.
But 0 TMS would be there, so I have 1, 2, 3, 4. 4 are very clear. What happened here? Did 2 of them overlap? Okay, and if I had to guess, just guessing, they're getting more similar the further away they are from this constituent. So the overlap might have been, I don't know, this and these 2, something like that. Something overlapped, and if you took that, and you could expand and zoom in on the NMR, you could just zoom in on that part, you would see that it's 2 peaks. but it's kind of squished here, so it overlap. Okay, how about this next one? How many?
1, 2, 3, 4, 5.
5, okay, let me see. There's 1, these methyls, 2, 3, 4, 5. So it should be 5, okay? There it is. And because of that nice electronegative group, things got a lot more spread out. So 1, 2, 3, 4, 5. And notice the heights are kind of all over the place. That's because we don't pay attention to integration, so don't worry about that. Okay? You can see the scale is just gigantic, 0 to 220. Okay, so what we have now are just some sample spectra, and we're going to try to, let's see. That's terrible.
Let's see.
You can see it?
Oh,
Yeah.
It's not like magnifying glasses.
There.
Yeah, 5 eye.
I want us to be totally in the dark here. Wow. Can you kind of see it now? Is it better? That's awful. 3-methyl-2-pentanone. I am going to try something. Hang on just 1 second. I'll show you guys a trick. You'll like this.
You're gonna try right now?
I'm going to try it right now. Not as I draw it.
That trick, that's like a long way. Oh, wow. I need to get this one.
And structure, predict C13. There we go. That's a pretty cool program. Now we can
Doesn't
see
need
it.
it.
I hope it matches pretty closely what's on here. Let's make sure. 1, 2, 1, 2, 1, and there. Yeah, so we're good. Okay. This makes our lives a little easier because it gives us the answers, but we can see it, so that's the important thing. I'm going to take this guy and spread it out a little bit. Okay, so now we can work with that. So, looking at this is much better. You can see it. The carbonyl is the easiest one. That's this one right here. It's going to be the most deshielded. That's the one down at about 212. So that's our carbonyl. And now, the way I would go is I'd pick the most deshielded one because that's easiest to recognize. Then I start working my way out. And as I work my way further from it, I'm getting more and more shielded. So the ones I would go to next would be the ones right next door. This CH3 right here, and that one right there that's a CH. So it's substituted with groups. And as we just talked about in answer to, I think it was Justine's question, when you start putting alkyl groups on, you start getting incremental shifts to higher parts per million. Okay, they're not so incremental in C13, but you can see that this CH3 and the carbon right there, the CH, are the next most deshielded because they're closest to the C double bond up. So there's 30, and that one's at 50 because it's more substituted. Okay, so it's that one and that one. And then we move even further out. The next one is this one. It's at 24. And finally, you're pretty far away. That's these methyls here, and they're showing up right there.
Question?
Yeah.
Will you be asking us to like draw molecules on a test for this kind of thing, or what kind of questions?
The kind of questions I would ask would be like, I might show you a spectrum and then give you a selection of 3 molecules and say which one is it, that kind of thing. Or you may be given a formula, a proton NMR, and a C13 NMR. And I would say, what is it? Okay? But I won't just show you, I wouldn't just show you a C13 and say, what's this molecule? You need other data to go with it. Aisha?
When you give us the C13 NMR, is it going to be like that or with the triplex tablets?
I do both. I do both. Sometimes I'll have you guys draw, it's a pretty simple molecule, I'll have you draw both the coupled and the decoupled spectrum. And so you have to draw triplets, doublets, things like that. Okay. But they're never that complicated because you can see, this is a good illustration, this molecule is not that complicated, but imagine if those things were triplets, doublets, quartets, whatever they would be, it'd get pretty messy in a hurry. So I won't have you draw those. Okay, let's park this off to the side and take a look at the next one. The ChemDraw in the hallway has this program, if you're interested in using it. So, let's see what, if our next one is at all visible. Just as terrible. Okay. So, 3-phenyl 2-butanol. We're going to cheat again. Okay, there they are. Okay, now, if you look at that table, you can see that benzene occurs at around 100-ish. And we're seeing here, all those benzene carbons are very, very close to each other. 128, 128, 126 there. And so that is this grouping right in here. Right here, that's all the benzene stuff. And there's generally quite a bit of overlap. So people typically don't say, okay, that benzene carbon is this one right here. They kind of just circle the whole blob and say, there's your benzenes. Okay. So we'll do that too. There's our benzenes. And we have, I'd like to stretch this out to actually see it. Let's go ahead and do that. Because we have some outliers that we need to talk about.
Is ChemDraw better at going from name to structure than from structure to name?
Yes. Yeah, structured name, it tends to get things goofy sometimes. What I want to do is, I can't see it. There's one that's 140 something, but I can't see it. Let's do the others, and then we'll come back to it. So, we have here, let's do the carbon with the OH on it, right there. Or is that going to be? Yeah, it's kind of all blobbed up here. It's got to be this one right here. Yeah, it's got to be the carbon with the OH around 70-ish. Okay, and then you can see the methyls are pretty low. They're pretty shielded, 16, 22. So those are your methyls right there. And methyls will pretty much always occur there unless there's something really electronegative right on them. Right about there. And this thing here at about 48 or so. Yeah, that's our CH right there. It's close to the oxygen. It's just the same distance as this methyl from the carbon with the oxygen, but it's got the influence of the benzene ring attached to it. And so it's pulling it a little further downfield than you might normally expect, right around there. So it's the same thing we saw with hydrogen. You have to look at both sides of what is attached to a carbon with a hydrogen to see what kind of the additive effect is. Same thing with carbon. I've got a group deshielding over here, a group deshielding over here. It's going to be really deshielded, more so than usual. Now the things that we should address, let's see, we have one, there's that methyl, that's one type. The carbon on the OH, that's 2 types. The carbon sandwich there, that's 3 types, 4 types, and then the benzene, right? So this easy part of the molecule we've taken care of. 1, 2, 3, 4. Look at this benzene, it's kind of spread out, right? And one of them is pretty far up, it's like at 142 or so. And it's really hard to see, but that's that guy right there. Yeah, that one right there that's attached is pretty far spread out. So there are a couple things going on there. The number one is more substituted, which pulled it out from the pack. And there is this electronegative substituent here, which isn't pulling it that much. You know, it's pretty far away to cause that big of a difference, but it's something. But there's the more substitution, and then as you go through your reading, you'll read about this anisotropic effect. It's a ring current. And the benzene, as those pi electrons in a circle, create ring currents. And those ring currents deshield, essentially, the parts of the molecule. And they can cause it to pull away. let's do our last one. Get rid of this. Hide this. I'll have to somehow make these darker. Okay. What if I could copy this? See how it does with this. Ah, there it is. Okay. Let's pull this over and stretch it out. This is our last one. Okay, here we go. The carbons involved in the double bond are the easiest to deal with. They will be the most downfield. And there are two different ones. There's one here and one here. And you can see that they're showing up right there. Okay? The next easiest one to deal with is probably the carbon with the chlorine directly on it. If you look at your chart, that shows up 50-ish, 40-ish, 50-ish, thereabout. It's going to be pretty de-shielded compared to the others. And that's that one right there. And then we have two carbons that are real similar. They're looking like they're methyls. They're kind of in that methyl region. And so that would be this guy and this guy. Okay.
The 136, is that being de-shielded one because of the chlorine?
You know, if there's no resonance structure you can draw, that's got to be the reason. Yeah, just shoved it down just a little bit.